So we're live. So the error function, this was number 8 in the homework, and I'll post this to somewhere in our course, is equal to this function here, and we were asked to calculate the error function of 2. And using Simpsons rule with n equals 6 intervals. First thing we do anytime we do any kind of approximation is we say, okay, how big is our subinterval? And so the width of the interval is 2 divided by 6 intervals gives me a width of 1/3. And so then I want to know, well, what do my x values look like? And so they end up being just k over 3 because I'm starting at 0, which is kind of nice. Then we have to isolate what is the function we're integrating. And my claim is it's that constant times e to the negative x squared. And so then it's just a matter of taking 1/3 of h. And since everything has the 2 over square root of pi, I didn't feel like writing that over and over again, so I factored that out. And then it's just a matter of plugging in the x values that we get. 0, 1/3, 2/3, 3/3, 4/3, 5/3, and 6/3 takes us to the end. And it took me 3 tries typing that into a calculator to get it to come out right. And eventually I got my calculator twice in a row to tell me it was around 0.99527. Yeah, it was very different than my first answer, yeah. I think instead of, like, I think I multiplied by 3 accidentally there, and then I screwed up some exponents. And I did it in a spreadsheet. I did it in GeoGebra. I did it with the silly Google calculator. That was painful on my tablet. And then they said, once you get that number, then come up with a bound on the error. And the only way to come up with the actual error is if you know the actual integral, right? But the ERF function does not have an antiderivative, so the only way to come about it is to approximate. Now, I did just go to Google and type ERF of 2. ERF of 2, and Google says, hey, I know ERF. And it said ERF of 2 is this number right here to, I don't know, like 10 or 12 decimal places. And the mistake, you know that crazy problem we did in class the other day? I was answering the wrong question. It didn't ask me to find an estimate on the error. It said find the actual error because we knew an antiderivative for that function. So all I needed to do is integrate the function, come up with the actual answer, and subtract my answer from the real one. I didn't need to find all those crazy derivatives and check to see when there was a max or a min. So, but it was fun. It was a nice exploration. All right, so back, where'd that sucker go? There's ERF over here. Yeah, so they told us that the fourth derivative of my function has a max of about 12. And so all I had to do is plug that into the error estimator for Simpsons rule, which says take your max of the fourth derivative times the interval width to the fifth divided by 180 times the number of intervals to the fourth. And I came out with about 0.00165 as the maximum error. If you take Google's answer and subtract it from mine, you get 0.00005, I think it is, roughly, which is definitely less than my error estimate, which is supposed to be the case all the time. The actual error is going to be less than what we estimate it to be. So what I spent a half an hour doing in class the other day with that other function is finding the estimate of the error instead of the actual error. And if you have an antiderivative, the actual error is easy. You just find the integral and subtract. Okay, so anyway, I'll post this for anybody that's not quite done with the homework and wants to see it. I have a spreadsheet version of this like yesterday I'll post too in our course. All right, let's move on to something else. We are going to look at improper integrals. Yes, improper integrals. Let's orient the board. And so we're going to start off with a problem called Gabriel's horn. Gabriel being the angel Gabriel. And he has a horn that is infinitely long. Ooh, I have sound there. Who's that? All right, it's gone. Okay, so first, just a note about improper integrals. They come in essentially 2 flavors. One flavor is when you have some starting number. Let's say we start at 2, and then we try to go to the right forever for some function with respect to x. The problem with this here is our definition of integrals relies on real numbers. Infinity ain't a number. So that's why we call this improper. So the way to deal with something like that is what we have to do is say, well, let's just pick some number and let's call it b and put it over there on the end and find the integral from 2 to b. And then after we find that, we take the limit of that result as b goes to infinity. Okay? So we have to throw in a dummy value there, find our antiderivative, plug in that dummy value, and then we take a limit for that dummy variable. And it could be it's the lower bound and we're heading to negative infinity. Okay? It could be we're going to positive infinity and negative infinity. So it could be we need 2 dummy variables to pull something like that off. Okay? The other kind of thing that can happen is if you try to integrate across a vertical asymptote. So for example, consider going from, I don't know, -1 to 2 of 1 over x squared dx. The problem with the domain I'm trying to integrate across is that x can't be 0 because I have a vertical asymptote there. So we would have to break this up into parts. We would have to say this is equal to the integral from -1 to, let's call it a, of 1 over x squared dx. And then we would have to take the limit of that chunk as a goes to 0 from the left-hand side. And we would have to add that to the integral from b to 2 of 1 over x squared dx. And we would have to take the limit as b goes to 0 from the right side. So those are the two kinds of improper integrals we see. If we try to integrate across some undefined value, we have to break it and treat it as 2 separate intervals with dummy variables, or if we have infinity as one or both of the endpoints. Okay, so those are the 2 situations we need to deal with. So we're going to start with one of these guys here. And the function we're going to look at is f of x equals 1 over x. And we are going to take a look at the integral as x goes from 1 to infinity of 1 over x dx. Infinity isn't a real number. You can't just plug it in. You have to approach it. And so we have to rewrite this with some dummy variable. So I'm going to let x go from 1 to a of 1 over x dx. And then after I find that antiderivative, I'll take the limit as a goes to infinity. So improper integrals need to be rewritten as limits of integrals. Hi, Ventura. All right, so I'm going to hang on to that limit as a goes to infinity, and then come up with an antiderivative here. Antiderivative of 1 over x, ln, yeah, so it's the natural log of the absolute value of x from 1 to a. And then plugging in our boundaries, I still have that limit waiting to get some action. We've got the natural log of a. Now I'm just going to put parentheses a because I know a is a positive number. It's greater than 1. And then minus the natural log of 1. Which I've always been fond of the natural log of 1. What's it equivalent to? 0, right? So ultimately we just need to say, okay, what is the limit as a goes to infinity of the natural log of a? Does anybody remember how the natural log function behaves? Yeah, it increases forever. So let's see, what's the derivative of the natural log? 1 over x. And if x is positive, is 1 over x positive? Yeah, so since the derivative of the natural log is positive, that means it's always increasing. If it's always increasing without boundary, then I have a problem. Okay, so since the slope is positive, and we could double check, we need a little more information than that, actually. What else would we need? We would need the second derivative also, oh yeah, that's not enough information, is it? I would just go with it for now. Yeah, so what did I find here? I found that this integral right here diverges. Do you remember diverging limits back from Calc 1? So divergence means the limit does not exist. And there's two ways a limit cannot exist. One, in this case, it increases without boundary. That's one way for a limit to not exist. And bound. And the other way a limit could not exist if it bounces around and never settles down. Okay. So if it kept jumping from 1 to -1, 1 to -1, that wouldn't exist because it's not fixed. It's got to be a single number. This isn't a number. All right, so that doesn't work. Just a quick sketch of this function. I'm sure we all know what it looks like. It has the point 1, 1, and then it drops with an asymptote of y equals 0, and it rises toward the y-axis that way with a vertical asymptote of x equals 0. And we've just found that the area from here that way forever is infinite. There's an infinite amount of area here. So as x gets bigger and bigger and bigger, we get more and more area forever and ever and ever. Does that always happen? The answer is no, it doesn't always happen. So another example, suppose we find the integral as x goes from 1 to infinity of 1 over x squared with respect to x. We have to rewrite that sucker to be the limit of some dummy variable. I'm going to use a again, of the integral as x goes from 1 to a of 1 over x squared dx. So let's see, that's really x to the -2, antiderivative for x to the -2. See, we increase the power, right? So that'd be x to the -1 times -1. Yeah, so I still have my limit hanging out front as a goes to infinity. Antiderivative is -1 over x, right? From 1 to a. Plugging in my boundaries, I get the limit, oops, missed an I there, as a goes to infinity of -1 over a minus -1 over 1. Cleaning that up a little bit, I get the limit as a goes to infinity of 1 minus 1 over a. Now, I can move the limit through a difference if both parts of the limit exist. Well, as a goes to infinity, 1 is just 1, no big deal. And then 1 over a becomes what? 0, so this is 1 minus 0, which is 1. So that's kind of cool. If we look at the function 1 over x squared, from 1 on, if we find all the area in that tail forever and ever and ever, it's exactly 1 unit of area. It's kind of nuts. Let's draw that just for fun. Ooh, maybe I'll ask GeoGebra to draw it. Or even better, I'm liking Wolfram Alpha lately. Oh, what's that integral calculator? Oh yeah, it can do that too, can it? Let's go bring, oops, stop it. Oh, I think I already did it on this one. Yeah, I gave it 1 over x squared. In the options, I told it to go to infinity at the top. And then it found an antiderivative, evaluated it. I'm assuming it didn't show any steps up here. There's really not much to show, is there? And then if we take a look at my function f, what is f star? Do they define that somewhere? Oh, the area function. Okay, yeah. Oh yeah, it's showing the area function there. And big F is probably the derivative. Yeah. So the blue function is 1 over x squared. And as we go to the right forever, what we're going to find is if you go forever, you'll get exactly 1 unit of area. If you stop somewhere, then you lose a little bit. How much do you lose? Well, actually, we know. You lose 1 over whatever you stopped at. So if you stopped at x equals 1,000,000, then that means you lost that infinite tail, which would have 1 over 1,000,000th unit of area, for example. Okay, so anywhere I stop, kind of cool. This basically tells me the error in my integral. Doesn't always work out that nice. Okay, we are now ready for Gabriel's horn. So sometimes improper integrals will converge, meaning that you get a real number in the end. You have a finite amount of area in an infinite space, which is kind of bizarre, isn't it? Finite area in an infinite space. On the other hand, sometimes you get an infinite amount of area in that space because you go to the right forever, for example, with the other function. So what we want to do is we want to take that function 1 over x from 1 to the right forever, and we are going to spin it around the x-axis. And that's going to build a horn for us. And it's going to go on forever that way. And we're going to do 2 things with this horn. We're going to calculate the volume of the horn, and we're going to calculate the surface area of the horn. So let's do the volume first, because that's easier. So for the volume of this horn, I would consider a rectangle like that I'm going to revolve. That means I'm using x as my variable of integration here. And when I revolve that rectangle, that's going to give me these little disks. I just need to know what is the radius of my disk to get the volume. What's the radius of my disk here? Almost. It's just 1 over x. Because the radius is the distance from my axis of revolution here up to the function, and the function is just 1 over x. So the radius here is exactly 1 over x. And so my disk here has a chunk of volume that's pi times the radius squared times the thickness of the disk, dx. And I want to accumulate all of those little disks. So that means my volume is going to be the integral as x goes from 1 to infinity of pi times 1 over x squared, if I clean that up a little bit, dx. So this integral represents the volume of this infinite horn. Okay, cool. All right, so the pi is a constant. I can pull that out. I do have a problem because I have an improper integral. Okay, so I'm going to pull the pi all the way out, and I'm going to make a note that I'm taking a limit. I'm going to let a be my variable again. So I now have the integral as x goes from 1 to infinity. Oops, no, I lied. I took the infinity out. What should it be instead? An a of 1 over x squared dx. So I make it a proper integral with a limit by using the dummy variable a. So what's that? Yeah, we already calculated this right here in the previous example. That comes out to 1. So that means Gabriel's horn must have pi units of volume. So maybe we're measuring in centimeters, then it would have exactly pi centimeters cubed. How long is Gabriel's horn? It's infinitely long, but it has exactly pi units of volume in it, right? So if we were to think about like painting Gabriel's horn, we could just fill Gabriel's horn with paint. How much paint would it hold? Pi cubic units of paint. Just kind of cool. Actually, pi as a decimal has an infinitely repeating part. Each of those values turns out to be, smaller and smaller and smaller chunks, right? At a millionth, a 10 millionth, a 100th millionth, and so on. But pi actually lives between, 3 and 4, very nicely closer to 3. So it's a real number for sure. It's just hard to write down in our decimal notation. So somebody say, well, let's use a different base. What about binary? Well, in binary, it's infinitely long too. No matter what base you pick, it's infinitely long. Yeah, pi is a sneaky one. I don't know what to say. Yeah, it would take a while to fill this up, even though it's pi, unless we consider like there's no friction and and angel time. I mean, they live in a different plane where time is irrelevant. So I'm sure for Gabriel this feels no problem. It just happens like that. He feels it with pain. Okay, so let's find the surface area now. Okay. So we can fill it with paint, but how much paint do we need to cover the outside? Okay, so let's figure that out. Surface area is a wee bit more complicated. So just a reminder of the formula. It's the integral from wherever you start to end of 2 pi times your y value, which is usually a function. And then we have that 1 plus y prime squared living inside of a square root because the Pythagorean theorem is hiding in there. And that would be a dx version of the surface area integral, which is good because we set up our previous one to use dx. So we're ready to go there. We have a little bit more work to do. So in order to do this, we need to figure out what y prime is. So let's see, y prime, see, that would be y is x to the negative 2. So it'll be multiplied by the power, negative 2 times x to the negative 3rd will be the derivative. Oh, it's 1 over x. I lied. Sorry, I'm in the wrong plane. Mention something like that. Okay, I better write down what y is. Let's back up a step there. There we go. Y is 1 over x. Okay, there we go. So y prime is going to be negative 1 times x to the negative 2, or we can consider it negative 1 over x squared. Okay, so then we have to square that sucker and add 1 to it. So 1 plus y prime squared isn't too hard here. It's just 1 plus 1 over x to the 4th. Okay, so, and I have to take the square root of that sucker. I think we're ready to just write the integral now. So we're going to have, let's write it in black, the integral as x goes from 1 to infinity of 2 times pi times our y is 1 over x times the square root of 1 plus 1 over x to the 4th dx. I think I got that right. Y prime squared, 1 plus. Okay, so now we got to hope we can clean that up. And we have to rewrite it as a limit. Before we do the limit, let's see if we can clean this up a little bit there so we can work with it. Oh, is this one of those, did we see something like this a while ago? This looks familiar. Like one of those problems I started because it looked challenging and I had to come back the next day with it. Let's see. So 1 over x, I would want to add the fraction in here. So the 1 would be x to the 4th over x to the 4th plus 1 over x to the 4th is going to become 1 over x times the square root of x to the 4th plus 1 over x to the 4th. Does that help at all? Oh, Maybe, maybe not. I can take the square root of x to the fourth. That's going to come out as x squared. So that'll be 1 over x cubed times the square root of x to the fourth plus 1. And I was thinking this looked promising because the derivative of x to the fourth is x cubed, but the x cubed kind of lives in the wrong spot. But it might work out. We'll give it a try. Yeah, I guess we'll give this a shot. Anybody have another idea before I proceed? What's that? You think it'll work? All right. So we're going to consider just this integral for now. And I'm going to do a u substitution where u is equal to x to the fourth plus 1. So then du is equal, I don't know if this is going to help, is equal to 4x cubed dx. Yeah, the x cubed. The x cubed is in the wrong spot. Darn it. We can't do that. Can't have a 1 over du. Darn. Not quite ready for that. We got to struggle a little more before we whip out that tool there. It's like, you know, if you're biking up a hill and like quarter way up, you decide to give up and grab a taxi. We're not ready for the taxi. Trig substitution? Yeah, maybe a trig substitution would work here. Let's try that. So let's see, should we do that here or there? Probably. Let's give it a try. Okay, so that failed. That's not going to work. So next suggestion is trig substitution. So if I'm going to do, I guess I'll stay in red. Trig substitution, I want to consider a triangle. And since this is a sum right here, that according to the Pythagorean theorem, a squared plus b squared equals c squared, then this must be related to my c. So I'm going to say c is the square root of x to the fourth plus 1. It's usually nice to put the x over here. In this case, since that's an x to the fourth, this is an x squared. And then this guy down here would be 1. Because Pythagorean theorem says square the legs and add them up to get your c squared. Okay, so if that's the case, what do we have here? We have that the tangent, I guess I should write it as x squared equals the tangent of theta, right? Because tangent of theta is x squared over 1. So then, I don't know about this. X would be plus or minus the square root of the tangent of theta. And let's see, cosine would be 1 over the square root. So secant would be equal to the square root. So I guess I should do my dx next. Dx, and can we just keep the positive version of this and not lose anything? What are our bounds of integration? We're going from 1 to infinity. Yeah, I think we can safely just use the positive version. So let's see, what's the derivative of the square root? Almost 1 over twice the square root. So it's 1 over twice the square root of the tangent of theta. And then we have to multiply that by the derivative of the inside, derivative of tangent, secant squared. Okay, what do you got?
Something to do with arcs.
Oh, an arc hyperbolic trig function?
An inverse.
Okay, we can look at integral tables. Let me just go a little farther on this, then I'll look up an integral table. I forgot we had those at our disposal. Let's see, where was I? secant. The square root of x to the 4th plus 1 is equal to the secant of theta. Ooh, this is crazy. And then I'm pretty sure we're okay with just choosing the positive version of that square root because of our x values. Yeah, x is a positive number here for sure. Okay, so substituting back in there, let's see, what do we got? Ooh, this is wild and crazy. Our dx is this whole chunk right here. Our square root is this guy right here. And then we need 1 over that guy cubed. Oh, that might come out okay. All right, you guys keep it close. Anyone have some of this written down? Maybe yes, no? Uh-oh, you guys are just watching? Oh, shit. Okay, so putting that all back together, I think what we have is 1 over the square root of the tangent cubed times our square root function is just a secant of theta times, and our dx was the kind of craziest piece, that was 1 over twice the square root of the tangent times the secant squared, right? Did I put it all together? I think so. I got that guy cubed, I got that guy, and I got that guy, yep. And I even remember to write my d theta. All right, so yes, so here, this is kind of cool. I have 3 square roots there and another square root there. That means I have the 4th power of the square root, which is just what? Tangent squared, yeah. I'm gonna pull out this 1/2 there. So I'm gonna have 1/2 the integral of the secant cubed of theta divided by the tangent squared of theta, which looks nasty. It looks terrifying. Yeah, that's pretty terrifying. Yeah, we cleaned it up quite a bit. Tangent squared is it secant squared minus 1? I can never get that minus plus 1 straight. Let's take a look. Secant squared minus 1. Yeah. I think we'd have to use integration by parts to continue this. Yeah, so that's one thing I was thinking. If we rewrote this as the integral of the secant squared of the theta times the secant, so kind of leave it the way it was up there. We have our tangent squared in the bottom. Oop, d theta, sorry. And if we let u be tangent, then secant squared d theta is our du. And if we combine that with an integration by parts, we might be able to deal with that separately. So I'm going to come back to that and take up Darren's idea and say, this might look like either this version or this one. No, I guess not that one. Probably this one here. Something in an integral table. And then if that doesn't look promising, we'll check out integral calculator or Wolfram Alpha. So let's see, resources. Which one do I want? Integral formulas. Okay, so square roots. Square root's in the wrong place on that one. And it's a difference. Oh, no, we don't quite have that because we have the 4th power. Yeah, but that doesn't match what's down here though, because on ours, where'd it go? We have, yeah, the u would need to be an x squared. It doesn't quite match. Oops. We might be able to use that with an integration by parts. So this, oh, there's this one here. Oh no, that's still u squared. Yeah, yeah, it doesn't quite line up. We might be able to use that with an integration by parts. So I think formula 70 with an integration by parts, or our trig stuff we have now with an integration by parts would probably work. So in the essence of time, because we're starting to run out, I'm going to ask Wolfram Alpha what it thinks. So let's see, which version should I give it? I guess I will give it the 1 over x cubed version, integral of 1 over x raised to the third times the square root of 1 plus x raised to the fourth. Does that look right? Double check. Yep, that'll work. Let's see what it thinks. Yeah, inverse hyperbolic function is involved there. Let's see, what did the integral table say? Integral table says natural log of 1 plus the square root, which is a hyperbolic inverse function. Probably the hyperbolic sine. Yeah, so it's given us a similar one. So let's just go with Wolfram Alpha's answer. Where'd it go? Right there. Okay, so we have an antiderivative. Let's see where it leads us. Ooh, inverse sinh of x squared. We're gonna have to look that sucker up. All right, screenshot. What's up? Let me grab that. So we want this guy right here. Now we have some constants we got to throw back in later. There's that 1/2 that we had pulled out. So yeah, this is looking, we would eventually got here. Okay. Now we were trying to take the antiderivative, sorry, the integral of this as x went from 1 to some constant a, and that constant a is going to go off to infinity. So we got to figure out what happens there. So we're going to have the limit as a goes to infinity of the inverse sinh of a squared minus a to the fourth, whoa, a to the fourth plus 1 in the square root over a squared minus, plugging a 1 in, we have a 1/2 times all of this. So that's going to be the, yeah, we'll bring that back in later. Let's see, inverse sinh of 1 squared, which is 1, minus, what's that going to give us? The square root of 2, when I plug in 1 here, minus the square root of 2. So we have to figure out what happens to this guy right here as a goes to infinity. So what's that? Be a plus square root of 2. Thank you. Sign error. Yep. Plus square root of 2. All right. So the square root isn't too bad. So provided the inverse sinh exists as a limit, the limit of the second part as a gets big, because a squared could be considered the square root of a to the fourth, right? Does a +1 really make a difference for big values of A? Answer is no, so those guys are the same. So this sucker right here is gonna go to 1. Now we just have to figure out what the inverse sinh does. So the inverse sinh is actually a logarithmic function. So let's get its definition. Probably definition. And it's hiding somewhere on this page. Where is it? There it is. Okay, it's the natural log of x plus the square root of 1 plus x squared. And our z is really an a squared, right? So now we have to determine what is the limit as a gets big of the natural log of a squared plus the square root of 1 plus a to the 4th. Well, would you agree that as a gets big, this whole thing gets big? And what happens to the natural log of a number that gets bigger and bigger and bigger? It goes to infinity. So what can we say about this particular integral right here? It's infinitely large. It diverges. It increases without bound. Which leaves us with a bit of a problem. It can hold pi units of paint, but that's not enough paint to paint it. What the heck?
Logic.
Yeah, so we have a little, so Gabriel has a very magical horn here. You can't ever have enough paint to paint it, but you can fill it with paint. And it holds the magical constant of pi units of paint. Crazy. Good luck, Gabriel. All right, that's enough for today. That was quite the workout. So this was a really good problem to look at because it reviewed half of what we've done this quarter almost. So we got to play around with substitutions, trig substitution, we get to look at integral tables, we get to use a computer algebra system, we get to review limits from Calculus 1. So let's see, what is today? Wednesday, is that right, the 15th? So we have a regular class session tomorrow. That's going to be review stuff. I'll do a couple of more of these problems. I did post a sample test. I don't know if anyone's taken a peek at it yet. It's like 3 times longer than the actual test can be probably. So the real test will be much shorter. I'll talk more detail about that tomorrow. I'm going to do a study session Friday, and then Monday is also a study session for anybody that wants to come. And then our exam is what? We decided Tuesday? Tuesday is going to be our real final. So thanks for playing. What time do we usually meet? 11. I think we're scheduled for 10, but 11's fine. I'm pretty open. I'm going to be here all day giving finals. Somebody emailed me that schedule. Let's take a look here. Stop the broadcast.